Okay, problem 2.8 in Wald's General Relativity. It gives us the metric of flat three-dimensional Euclidean space in Cartesian coordinates, and gives us some relations between Cartesian and spherical polar coordinates, and then we're meant to show that the line element, the equivalent line element in spherical polar coordinates is what's shown at the bottom there. So this isn't too hard, just a lot of algebra basically, so let's get started. Write our line element down. And then also the relations that were given. So let's go here. R squared equals x squared plus y squared plus z squared. We have that cos theta equals z over r. Now what our goal is going to be here is going to be to get the x, y's, and z's each in terms of only the spherical polar coordinates, because we're going to want to evaluate essentially this dx, this dy, and this dz in terms of those. So that being said, let's right away here just say that that z is r cos theta, because that will make our life easy later. And then we also have this tan relation, so tan phi is y over x. I choose to write that this way. X equals y cotangent of phi. I'm not going to put a box around that yet because we still have the y in here, notice, and we want to get this strictly in terms of the spherical coordinates. So let's work towards that. One way of going about getting something interesting is just substituting into this r squared equation. So let's go ahead and do that. We have something for x, so let's put that in. It's y squared cotangent squared of phi for x squared. And then just plus our normal y squared here, plus z is r cos theta, so r squared cos squared theta, and that is that line. Okay. So now we can go ahead and factor out the y squared term, because the brackets are going to look like a trig identity kind of now. Scroll down a little bit. So let's simplify these brackets a little bit now. So we're going to have something like, let me think. Plus 1, which means we can just add sine squared phi on top. So this is actually the top is gonna go to 1, and that's 1 over sine squared phi. We can see right away. So let's write it that way. Oops. So we have that r squared is y squared over sine squared phi plus r squared cos squared theta. Now let's group the r's together, so take this term over to the left side, or actually we can kind of change the direction of this too just to clean things up. So let's say y squared over sine squared phi is r squared 1 minus cos squared theta. Of course, the term in the brackets is nothing other than sine squared theta, so we can rewrite it's y squared equals r squared sine squared phi sine squared theta. And let me just double check that that is right. It is. Okay, so now we have y in terms of strictly these spherical coordinates as well. So we'll put a box around that. And then it just remains to do z, I think. So let's just remind ourselves what we have for z. No, z is okay. We need to do x. So x equals y cotangent of phi. X equals y cotangent of phi. And actually we should write our y unsquared here. I don't know why I put a box around that. We should actually look at y equals r sine phi sine theta. This is what we're mostly interested in. There we go. Okay, so this means that x equals, we're going to substitute in y, so we get r sine phi sine theta times cotangent of phi. And that means that x actually equals r of r cos phi sine theta after simplifying the cotangent. And now we have all three in terms of only the spherical coordinates. So I'm going to write those all down here. We have x equals r cos phi sine theta, y equals r sine phi sine theta, and z equals r cos theta. So now with this, we can basically just use a chain rule idea to expand for the differential elements. So dx, for example, is just going to be dx by dr plus dx by d theta plus del x by del phi d phi. So in terms of r, we get the cos phi sine theta times dr plus dx by d theta is going to give us our r cos phi cos theta and then minus r sine phi sine theta. Oh, and I'm forgetting to put the differential elements here, so this is going to, this one has dr, but this one is going to be d theta, and this is going to be d phi. Okay, and I'm not going to bother squaring that here. We're just going to write these as, write the linear relations. So that's good. I'm not going to write down the chain rule for the next ones. We're just going to go ahead and do it. So dy equals sine phi sine theta dr plus r sine phi cos theta d theta plus r cos phi sine theta d phi. And finally, dz equals cos theta dr minus r sine theta d theta. Now all that's left to do is square each of these expressions, add them together, and simplify that. I am not doing that by hand. I plugged mine into Mathematica and simplified that way and was able to show that it matches the line element shown at the bottom of the problem here. So that was my complete proof. If you guys want to work this out by hand, you certainly can, but it's very time consuming and not very illuminating, I don't think. Okay, so we can start on part B now, where he gives us the space-time metric of special relativity, which looks the exact same as in part A, except for we now have this minus dt squared term here. And Wald wants us to find the components of the metric and the inverse metric in rotating coordinates, so he gives us these relations between the primed and unprimed variables. Yeah, and we just got to compute the metrics, so let's go ahead and do that. I put this down here just for convenience sake. And it's going to be similar to the last problem, right? We're going to want to get these unprimed variables in terms of the primed ones if possible, so let's just start looking at combinations of of these. So we can start by thinking about x prime squared plus y prime squared and what that's going to give us. And so we're going to get x squared plus y squared out front on both terms. The square root goes away because of the squares. And then cos squared phi minus omega t plus sine squared phi minus omega t. But the inside of these brackets is just 1. So we get our first useful relation that x prime squared plus y prime squared equals x squared plus y squared. Okay, now we consider another combination. Let's think about y prime divided by x prime. So right away, the square root terms are going to cancel out, and we're just going to get cos phi minus omega t. Oops, it's supposed to be a sign on top. Sine phi minus omega t divided by cos phi minus omega t, which is just tan of phi minus omega t. Okay, but let's remind ourselves, so this means y prime over x prime actually is tan of the inverse tan, because of what phi is, of x, y prime over x, y over x, sorry, not primed, y over x. Let me just double check that that's right. Yeah. Minus omega t. So this means that we can take this tan over to this side. Inverse tan of y prime over x prime is the inverse tan of y over x minus omega t. So with this, y over x is just, let me think, the tan of the inverse tan of y prime over x prime plus omega t. And now we're going to actually rename t to t prime because they're the same thing, and we want these in terms of the prime coordinates. So this is a pretty good start. Oops. Okay, now we can combine these together kind of. So let's write the other relation here just so we have it. Okay, so we have x prime squared plus y prime squared equals x squared plus, and then let's just put in y squared. So bring this x to the other side and square it. X squared tan, actually, and I'm not even going to write the inside of this, I'm just going to put the tan of the mess, and we're going to carry it around like that. So let me think here. We can factor out the x squared. And then we can find a relation here saying that x squared, just scroll down, equals x prime squared plus y prime squared over 1 plus tan of mess. And this is just x prime squared plus y prime squared over secant squared of the mess, just by trig identities. So with this then, x is going to be the square root of x prime squared plus y prime squared times cos of the mess, but we can actually write this now, so tan to the minus 1 y prime over x prime plus omega t prime. Now we're going to use another trig identity, so we know that cosine of alpha plus beta is cos alpha cos beta minus sine alpha sine beta so we can rewrite x as the square root. I'm not going to fill in the inside for now. Actually, no. Now the cos of the inverse tan is going to give us something like this. This is another trig identity that you can just look up. So let me just find what I'm doing here. Cos of inverse tan of y prime over x prime is going to be 1 over the square root of y prime squared over x prime squared plus 1. This is going to be times cos of omega t prime minus, and then the sine of the inverse tan is going to give us something like this. Again, just look this up. Y prime squared over x prime squared plus 1. Oops. Times sine of omega t prime. Okay, so now we're going to rewrite this again. This time I'm going to explicitly put the x prime squared plus y prime squared out front just so we can see what we're working towards canceling with. Get a 1 over x here because we're going to pull that out of the square root. And we get a y prime squared plus x prime squared in here. And on top, I guess I could write this, the cos of omega t prime minus y prime over x prime 1 over x square root of y prime squared plus x prime squared. So again, we're just putting this into a nice form so that we can cancel with the square root up front. And then we're going to get the sine of omega t prime up here. So we can go ahead and make that cancellation now. This is going to equal x times cos of omega t prime. Sorry, these should be primes. This should be x prime. So x prime of cos omega t prime. Then this 1 over x is going to cancel with this x, and we get minus y prime of sine omega t prime. Put the brackets here too. So this is x, and then we can follow a similar lengthy procedure for y. So we can go ahead and do that now. So we can write instead, let me remind myself. We have y over x equals tan of the mess is x tan of the mess. So that means x equals y cotangent of the mess. Okay, and then we have this relation again that we used for the last one, but this time we're going to substitute in for x instead. So we get y squared cot squared of the mess plus y squared we can factor out the y. Oops. And then this means that y squared is x prime squared plus y prime squared over cot squared of the mess plus 1. But remember, cot squared plus 1 is just CSC squared of the same thing, so let's write it that way. And finally, then we can simplify this. Okay, so that's looking kind of similar to what we had before. So let's write this here. We'll say y squared is, oops, not y, yeah, no, that's right. Is, let's see, x prime squared plus y prime squared actually, let's put this square like this. And now we can use another trig identity that sine of alpha plus beta is going to be sine alpha cos beta plus cos alpha sine beta. So y then is the square root of x prime squared plus y prime squared times, and then we're going to do this trig expansion here. So we're going to have sine of inverse tan of y prime over x prime times cos of omega t prime plus cos of tan to the minus 1 y prime over x prime times sine omega t prime. Now the sine of the inverse tan is going to, well, actually, let's write this first. So equals, we're going to have the square root here. And the sine of the inverse tan is going to give us something like this, that identity from before. And the cos of the inverse tan is instead going to give us something like this, just 1 over the square root of this. And we're going to make a similar cancellation to last time, so let's set it up for that. out that 1 over x prime here, and then get the square root of y prime squared plus x prime squared. And then here we're going to have the cos omega t on top still, or omega t prime rather. And then same deal here, 1 over x prime square root y prime squared plus x prime squared. And this can actually be sine of omega t prime. Now we're free to go ahead and make the cancellation again. So we'll do this. This x prime will cancel with this x prime, and we're left with something relatively simple, that y is y prime cos of omega t prime plus sine, x prime sine omega t prime. Okay, so we have our x and our y now, and we're pretty close to the end of this problem. So I'm going to rewrite x here just so we have it. Oops. There we go. So now all that remains to do is calculate our dx and our dy and go from there. So let's go ahead and do that now. So remind ourselves that dx by the chain rule is going to be something like this. Oops, I'm writing this wrong. Dx by dy prime, dy prime so trivially, some of this is going to be 0, but let's go ahead and calculate it. So dx by dx prime is going to be cos of omega t prime times dx prime. Dx by dy prime, we're going to get minus sine of omega t prime, dy prime. And then the t term is going to be a little more complicated. So let's say plus minus x sine omega t prime minus y prime, this would be prime 2, cos omega t prime, and this whole term is going to have an omega, and then dt prime. And then dy we can calculate similarly. So I'm going to just write this out here. And now what we want to do is, actually I'll put a box around this, so dy And what we want to do now that we have our dx and dy, we're good because we already have our dz and dt trivially here. These relations are very simple. So with this, we just want to consider the combination that makes up our line element. So we want to consider minus dt squared plus dx squared plus dy squared plus dz squared. And you can do this by hand with the terms that you've calculated up here, squaring them and simplifying things. Instead, I just put this directly into Mathematica at this point because I'm too lazy to do this much algebra. But if you do it, it's going to come out to be minus dt prime 1 minus omega squared x prime squared minus omega squared y squared prime, obviously, plus dx prime squared plus dy prime squared plus dz prime squared, and then some cross terms, minus 2 dt dx omega y prime plus 2 dt dy omega x prime. So this matrix, or this metric as a matrix, has to be symmetric, obviously, so the way that we write this is like this. So that's our TT element. A little bit sloppy, but it does the job. Okay, good. So that's basically the end of the problem. Wald also asks to invert this matrix, and so we can get the inverse metric, but that is a lengthy process of just like matrix calculus that I didn't feel like doing either. So if you want to go ahead and use Gauss-Jordan elimination to do that and show it by hand, you can. I just did the Mathematica thing again, and I will just show my result on screen just for anyone who does want that answer. This is the form of the inverse matrix right here at the bottom.